Today, we're going to dissect a topic that seems foundational, but is actually one of the most diagnostically challenging entities in all of electrocardiography, the atrial premature beat, or APB. You'll also hear it called a PAC. Now, this is an incredibly common finding, but the way it manifests can be so profoundly deceptive, it can throw even seasoned clinicians for a loop. Let's really dig into the electrophysiology of why that is.
So here's how we're going to break this down. First, we'll establish the fundamental definition of a PAC. Then, we'll get into the absolute core mechanism, the refractory period, which is the key to understanding all its various presentations. From there, we'll visualize the three distinct conduction pathways they can take: normal, aberrant, and blocked. And then comes the most clinically relevant part, how PACs act as great mimics of other more serious pathologies. Finally, we'll consolidate all of this into a set of key diagnostic principles that you can apply.
All right, let's begin with the foundational concept. Before we can appreciate the complexity, we need to have a very precise definition of what it is we are analyzing. So, what exactly is an atrial premature beat? At its core, an APB is simply an electrical impulse that fires from somewhere in the atria that is not the sinus node. And the key property, of course, is that it occurs prematurely. It arrives earlier than the next expected sinus beat. But here is the absolute crux of the issue. The fate of that premature impulse, and thus its appearance on the ECG, is entirely determined by the electrophysiological state of the conduction system at the precise moment it arrives. Is the system receptive, or is it still recovering? And that leads us directly to the single most critical concept for understanding APBs, the refractory period. If you can internalize this principle, all the downstream manifestations will become perfectly logical. This diagram illustrates the entire principle beautifully. You can think of that shaded curve as the recovery phase, or the recharging period of the ventricular conduction system after a beat. A critical physiological detail is that different parts of this system, namely the right and left bundle branches, recover at slightly different rates. The arrows, labeled A, B, and C, represent our premature atrial impulse arriving at different moments during this recovery phase. And as we're about to see, that timing changes absolutely everything. So based on that timing, there are only three possible outcomes for our premature beat. First, if the impulse arrives relatively late in the cycle, at point C, the entire conduction system has had time to fully repolarize. It's ready. The impulse conducts normally, and you get a narrow QRS complex that just looks early. Now, if it arrives a bit earlier, at point B, things get interesting. One of the bundle branches has recovered, but the other one is still refractory. So the impulse travels down the recovered one and then has to spread slowly, cell to cell, to the other ventricle. This creates a wide, bizarre-looking QRS. We call this aberrant conduction. But if the impulse arrives very early, at point A, it hits a system that is still absolutely refractory. It's like hitting a brick wall. The impulse is extinguished in the AV node or his Purkinje system, it never reaches the ventricles, and no QRS is generated at all. Okay, so let's transition from the schematic diagram to clinical reality. Let's see what these three distinct electrophysiological events actually look like on an ECG tracing. This single rhythm strip is an absolutely perfect teaching case because it displays all three potential fates in one continuous recording. First, look at the beat labeled A. You can see a premature P wave followed by a normal, narrow QRS. That's our normally conducted APB. Now find the two beats labeled B. Notice how wide and morphologically different they are from the sinus beats. Those are our aberrantly conducted APBs. Finally, look at where the arrows are pointing. You can clearly see a premature P wave, but it's followed by nothing, just a pause. That is the non-conducted or blocked APB. All three possibilities, one after another. And let me just emphasize a critical point here. When you see that wide, aberrantly conducted beat, your first instinct might be to call it a PDC, a ventricular premature beat. But it's not. The origin of the impulse is still supraventricular. It's atrial. The wide morphology is purely a result of that physiological difference in refractory periods between the bundle branches. It's a rate-related conduction delay, not a ventricular ectopic beat. This latter diagram provides a fantastic schematic for what's happening during that non-conducted beat. You can trace the impulse starting in the atrium, the top tier labeled A. It successfully propagates down into the AV junction, the middle tier. But then it just stops. It encounters that fully refractory tissue and simply cannot proceed. The impulse never reaches the ventricles, the bottom tier V, and that's precisely why no QRS complex is generated. And this brings us to the most clinically significant portion of this analysis. It is precisely because of these varied manifestations, and most importantly, the non-conducted beat, that APBs are famously known as the great mimics. They can create ECG patterns that perfectly replicate other, often more serious cardiac conditions, leading to profound diagnostic errors. So let's put this to the test with a diagnostic challenge. You're presented with the following ECG. The clinical question is this: are you looking at a simple, benign sinus bradycardia, or could this be evidence of pathologic sinus node dysfunction? Now, at first glance, the diagnosis seems obvious. The ventricular rate is clearly slow, and you can see these long, conspicuous pauses between the QRS complexes. It would be very easy and very common to interpret this as sinus bradycardia, or perhaps even episodes of sinus arrest, which would raise concern for sick sinus syndrome. But now, look closer. The entire diagnosis hinges on something hidden in plain sight. Look at the T wave immediately preceding each pause. Do you see it? Indicated by the arrows, there is a subtle deformity, a little notch on the T wave. That is a hidden premature P wave. This is not sinus node dysfunction at all. This is non-conducted atrial hegemony. Every sinus beat is followed by a blocked APB, which resets the sinus node and creates the pause. The sinus node itself is functioning perfectly. The apparent bradycardia is a complete illusion. Let's try another, even more subtle case. Here we see a sudden change in rhythm. The question now becomes, could this represent a 2-to-1 sinoatrial block? So on this 12-lead, the heart rate abruptly doubles. This pattern could certainly be consistent with something like sinus node reentrant tachycardia, but if you take out your calipers and measure the R-to-R intervals, you'll find that the long cycle is almost exactly double the short cycle. This precise mathematical relationship is a classic textbook feature of 2-to-1 SA block. So now we have two very plausible but competing diagnoses. So how do we solve this puzzle? We proceed with logical deduction. We have one clue suggesting a reentrant tachycardia. We have a conflicting but very strong clue suggesting 2-to-1 SA block. But what is our cardinal rule for any unexplained pause or irregularity? We must meticulously scrutinize the preceding T wave. And if you do that, looking exactly where the arrows are pointing, you will find it, a very subtle premature P wave deforming the terminal portion of the T wave. The diagnosis was neither of our initial hypotheses. This is simply another presentation of non-conducted atrial hegemony, creating a pattern that mimics SA block. These clinical vignettes lead us to our final and most important section, distilling these observations into a set of key diagnostic principles that will allow for accurate interpretation. Let's crystallize the main takeaways. 1. An APB has three fates. It can conduct normally, aberrantly, or be blocked entirely. 2. It is the non-conducted APB that is the great mimic, creating pauses that are frequently misdiagnosed as sinus node dysfunction or SA block. 3. The unequivocal key to the correct diagnosis is the identification of that premature, often hidden P wave. And this all culminates in the single most important, inviolable rule of ECG interpretation. In the face of any unexplained pause, irregularity, or bradycardia, you must meticulously scrutinize the morphology of the T wave of the preceding beat. That is where the truth is most often found. And we'll leave you with this final thought to consider. If an entity as common and seemingly benign as a PAC can create such profound diagnostic confusion, mimicking serious underlying disease, well, it makes you wonder, what other arrhythmias might we be misinterpreting? It's a powerful reminder that in electrocardiography, the devil is always in the details, and a meticulous second look is never, ever wasted time.